and a functor f in this direction and a functor g in this direction. And I said that f was adjoint, left adjoint to g if you had some natural isomorphisms morphisms from f of x to y, and this is happening in D, being naturally isomorphic to morphisms from x g of y. This is happening in C. Here x is an object in C, and y is an object in D. And these were natural in the sense that if you had morphisms in C and you had morphisms in D, then, well, this natural transformation, this natural isomorphism was compatible with those morphisms. We wrote some diagrams that commuted. But in particular, we looked at the example where if we take y to be some f of x, for example, then on the left-hand side, we had the identity of f of x. Right? This is an element in Hom, f of x, f of x. And under that isomorphism, it gives me an element in Hom in C from x into g of f of x. So for any object x, we have, for every x, whenever we have a pair of adjoint functors, we get a map, a morphism from x to g of f of x. Right? So this guy here, which is just the image of the identity of f of x under that isomorphism. So this I wrote in a different way. I said that this is the same thing as a morphism from the identity functor in the category C to the functor g composed with f. Okay? So if I do, am I doing this correctly? That's correct. So if I do f and then g, that's a functor from C to C, and then the identity of C is a functor from C to C, and then this is a morphism of functor. And similarly, by taking x to be g of y, we obtain a morphism from f composed with g to the identity functor in D. So that was the upshot. So in other words, for every object y in the category D, we've obtained a morphism from f of g of y into y, which is the image of the identity of y, which is now an element here under this isomorphism.
Can you show me why it is a functor?
Why?
Identity from C to G.
Why? Oh no, this is not a functor. This is a morphism of functors. So let's review that. Let's spend some time reviewing this. We have time. I decided that today I was going to have it lightly. So let's repeat that. Okay? So whenever you have two categories, here is C and D, I'm going to look at a new category, which is going to be the category of functors from C to D. Let's choose different names now, not to be confused with those C and Ds. If I have any two categories, let's say A and B. So let's suppose that A and B are categories. Then I'm going to define a category whose objects are going to be functors from A into B. So objects of this category are going to be functors f that goes from A into B. So now I need to tell you what are morphisms in this category. So suppose you give me two functors, f and g. There are both functors now from A to B. So now a morphism from, so what I need to do is to define this set hom in this category of functors from f to g. Now this set, I'll define it to be the set of natural transformations. Is English all right, or? Thanks. Okay, so I'll define this set to be the set of natural transformations. And I'll keep the word set for a minute. All right. So what is a natural transformation? Which is going to be an element of this set. That's going to be the following. For every object x in A, then I'll have hx, which is going to, what do I have, right? So when I have an object in A, what I have is the following. I can look at the following. I can look at f of x, and I can look at g of x. These are now two objects which are in B. And what I can do is look at a morphism between these two. Okay? And I'll call this morphism hx. Right? So for any object of A, I'll just have one hx, which is going to be a morphism between f of x and g of x. This morphism is in the category B. Now suppose that you have a morphism in the category A from x to another object. So let's suppose that now you take x prime to be an object in A, and you have some phi, which is a morphism in the category A from x to x prime. So now, since f and g are functors, then you have a morphism from f of x to f of x prime, which is called f of phi. And you have another morphism from g of x to g of x prime, which is g of phi. And between these two objects, since I had such a thing for any x, then here I have a morphism, which is h sub x prime. So now a natural transformation would be the following data. For every object, you give me this hx, such that for every morphism phi, you give me a commuting diagram. Okay? So that's called a natural transformation. So that's going to be my set of morphisms from f into g. Right? So this set, I'll define it to be the set of natural transformations okay, as I just defined it, from f into g. So now what we need to check is that with this definition, we have a category. So there's lots of things to check. So for example, I need to check that I have identities here. Right. So if I have f, I need to check that I have a particular element which is the identity of f into f. Right? So I need to construct such a natural transformation. But that's clear what it is. So for every x, I just define hx to be the identity morphism of f of x, which is an element in hom from f of x into f of x. And that clearly fits into this diagram. Here I have g is equal to f. I just chose the identity here. Of course, this here is going to be the identity of f of x prime, and this diagram will commute. So the identity gives me a particular element that I will call the identity natural transformation. Okay, so that's going to be the identity of f. So now I need to tell you how to compose these morphisms. I need to have composition, and I need to check that it's associative. Okay? So now suppose that you have some H, which is a morphism from F into G. And suppose you have some K, which is a morphism from G into H. Right? So now here we have F, G, and H are functors from the category A into the category B, and I have two morphisms, H and K, and I want to compose them. Right? So what I need to tell you is what is the composition of K composed with H that should be an element, a morphism between F and H. Okay? So now what is a morphism between F and H? By definition is for every object what you need to construct is a map from, is this guy, is K composed with H sub x, which by definition is an element from f of x, is a morphism from f of x into h of x. But we have some data already. We have a map from f of x into g of x, which is what h gives me. H sub x, by definition, is such a map. And k sub x is, by definition, this map. So I can just define this guy to be the composition. So I'll define this guy to be the composition of kx composed with hx. Okay? And now I need to check that this guy satisfies this commuting diagram, but that's trivial. So I need to check that this composition defined this way satisfies that commuting diagram, which is clear because if you have a morphism between x and x prime, this is going to be my f phi. Here phi as there is a morphism between x and x prime. Then you have here a morphism, you have this commuting diagram. Now here you have a map from g of x prime, which is g of phi. This diagram commutes. This is h of x prime. Here you have a map to h of x prime. Here you have this map, which is k of x prime. And this diagram commutes. So this because h is a morphism, this because k is a morphism. Okay? And now this composition and this composition, now this big diagram commutes. And that by definition means that this guy here is a natural transformation. Okay? So now I just defined you the composition. So exercise, check that it's associative. So now I need to check that. Okay, so I need to check that if I have a third morphism, HKL, so if I have some L, which is a morphism between H and L, L is another functor. Now you need to check that L composed with K composed with H is equal to L composed with K composed with H. I have two different compositions and I need to check this. So that's not hard.
Directly from functor B?
Sorry?
Can I say that equation you can get directly from the definition of category B?
Of the category B?
Because every hx belongs to the homomorphism B from F.
Oh, yeah, that's right. So when you spell it out, so here you're going to have to use the associativity of composition in the category B. That's correct.
I mean, can you directly just from
I don't see how, at least.
because it's composed, the composition is in the category B, right?
The composition is, that's correct, but that composition depends. Yeah, so we have one composition for each object X. Yeah, so Probably what we're calling direct is not the same thing, but yes, it follows from associativity of composition in the category B. And you also need to check, so the exercise 2 is check that you have identities. So the identity of F is an identity for the composition. These are not hard exercises. It's just simple exercise to check that that identity as I defined is an identity for the composition. And again, it's because it's an identity in the category B. However, there's a subtlety that I don't want to deal in this class, and it has to do with the fact that for categories to be well behaved, this has to be a set. Whenever you have two objects in a category, the set of morphisms in particular has to be a set. And I've never proved that the collection of natural transformations is a set.
Everything you use is nature of set.
Are you sure? Objects in A and objects in B might not be sets. So in particular, this H, right? So the collection of objects of A and objects in B might not be sets. When the objects of a category form a set, that category is called small. And the notion of natural transformation as I defined is an assignment for each object in a category, which is already, this is not a set, not necessarily a set. So I'm not going to get into details to those details. I'll just assume that we have sets. You can assume that your categories are small enough in such a way that this is a set. Of course, if the category A is small, so if the objects of the category A form a set, then there's no problem. And it doesn't matter how large the category B is. But that's just a subtlety, and let's just not deal with that subtlety. Let's just forget about set theory arguments. Now, what happens? What is the situation when we have two functors that are adjoint? So here, I don't have A and B. I have C and D. And I have this functor F from C to D, and this functor G from D to C. Okay? So now, in particular, the identity of the category C there is a functor from C to C. So now this is my A in that board, and this is my B in that board that are equal. And the composition of G composed with F is also a functor from the same category, from C to C. Right? So both of these guys that are functors are both objects in the category, are both objects of the category of functors from C to C. This is the category of endofunctors from C to C. And I just spelled two boards defining what morphisms in this category were. Okay? And a morphism in this category, by definition, is for every object X, you need to give me a map from. Right? What is a morphism? So for every object X in the category A, which is C, you need to give me a map from X into, so this is what I was calling HX. Oops, it's not X. I need to give you a map from this functor, which is the identity of C applied to X, to this functor, which is G composed with F applied to X. And the identity of C applied to X, this is just X. Right? So I need to give you this map. And that's what the adjunction gave me. So whenever we have F left adjoint to G, we've obtained a morphism in this category between this functor and G composed with F. And now we also have functors the other way around. We have F composed with G. Now here A and B are going to be D. This is an endofunctor from the category D into D. And we have a map to the identity of the category D. Okay? So that's whenever we have a pair of adjoint functors. Now, two categories, I'm just repeating last class. Two categories are said to be equivalent C and D are said to be equivalent if there exist two functors, one from C to D, one from D to C, such that the identity functor in C is isomorphic to the functor which is G composed with F. Right? So these are two functors in the category of endofunctors from C to C, and I want them to be isomorphic. And the identity functor in D is isomorphic to the functor F composed with G. So in this situation, we say that F and G are an equivalence of categories, and we typically call G to be F inverse. And what we see is that whenever we have an equivalence of categories, the two functors, a functor and its inverse, are adjoint. And moreover, we have both adjunction. F is left adjoint to F inverse, and it's also the right adjoint to F inverse. Notice, but this is important. The point is that whenever you have two categories that are equivalent, you have a more. So what does it mean for these two morphisms these two functors to be isomorphic? So let's spell that out. What does this mean that we have this isomorphism? So this symbol here of isomorphism, what does it mean? Right? So now, on any category, what does it mean to have an isomorphism? It means that you have two morphisms. Right? For this to be an isomorphism, it means that you have two morphisms from the identity of C to G composed with F. We want to have a morphism here. Let's call this morphism H. And we want to have another morphism from this object to this other object, which is on the same category. These objects are objects. Everything here is happening in the category of functors from C to C. And I want to have another morphism here, K, such that the composition of these two morphisms is the morphism identity that I just defined there. Is the morphism, which is the identity morphism in the category of functors from C to C. Okay? Okay. So what does this mean now? So having these two morphisms and the composition is this, well, now you spell it out. It means that for every object X in C, this morphism here, we have an H of X that is a morphism from the identity of C to this composition. Therefore, it means that we have a morphism from X to G composed of F with X. And we have some K of X, which is a morphism from here to here, from G composed with F of X to X. And what we want is that the composition of these two morphisms is the identity of X. Okay? So this means that, well, since this composition is the identity of X, it means that H of X is an isomorphism between X and G composed with F of X, and K of X is an isomorphism with G, F, X with X, and they're the inverse of each other. So there's two levels here. For this to be an isomorphism, we need, for every object X, an isomorphism between these two objects. Okay? And equality only happens at the second level, that the composition of these two things is equal to the identity. I could have defined that the composition of these two functors being equal to the identity functor of C, not isomorphic. That's well-defined notion. I have two functors between the same category. I can ask when these two functors are equal. And when these two functors are equal. That's the usual notion of definition of isomorphic objects. So when that happens, I would say that C is isomorphic to D as categories, which is different than equivalence. Equivalence is a better defined notion for categories. Isomorphisms is a badly defined notion for category in the sense that there are no naturally isomorphic categories. Okay, so that was essentially what we did last time. And I wanted to give some examples and relevant for the situation we are, which is we're studying representations of groups. So there are two examples. One is the adjunction of hom with tensor products for modules of commutative rings, which we defined. And now I want to talk about induction and restriction functors on the categories of representations of different groups. So the situation, I'm not sure if this is the same notation that I used last time, but the situation is that we're going to have some H being a subgroup of G finite groups. We'll fix some ground field. Let's not worry about characteristics, so let's just choose that the characteristic of K being 0. And what we have is some obvious functor from the category of G modules to the category of H modules. That I call this functor the restriction. And again, I'm not sure if this was the same notation I used last time, but I'll call this functor the restriction from G to H. I might have switched H and G there. So what is this functor? Whenever you give me some G module W, okay, so what is a G module? This is, by definition, rho is a map from G into GL of W. Okay? But now, let's call this inclusion of H in G iota. So then we map this to the same vector space W, and the morphism is just rho composed with iota. So I have H with iota to G, and then rho to GLW. So it's just simply remembering how H acts in W. And the question is, how do I construct adjoint functor? Does there exist an adjoint functor to this functor? Okay? So then we'll get back later to when we might expect to have adjoint functors. But the question is, does there exist some functor the other way around from here to here? And I constructed two last time, and I want to discuss them both. I constructed two that are the same, but I want to see them for a little time as different. Right? So the other functors are going to be called induction. And I'll use two different names. I'll use induction and induction prime. So this is going to be an induction from H to G. So what is the induction functor? We can do this in two ways. The induction from H to G of V now is an H module. I'll define it to be the vector space K of G tensor over K of H with V. And I'll define another induction. Let's call this induction. I think I used tilde last time. from H to G of V to be the vector space of functions. And I'm not sure if I chose this particular, I mean, there are some different options that you can check to get here. So I'll just, let me write it like this. I'll write it as F from G to V such that F of, I think I'll use A, B is equal to rho of A acting on F. Oh, my rows and my F's are the same. So let me just not use rho. It's equal to A acting on F of B for every A in H, B in G. Right, so our functions, here I'm using, in this symbol here, we're using the action of A, which is an element in H, and on F of B, which is an element in V, which is an H module. Therefore, A acting on F of V makes sense. Okay, so let's start analyzing the second induction. Okay. All right, so first of all, notice that, I mean, in here, this is obviously a vector space. It's a K vector space. But in here, this is, a priori, it's not. These are just functions from G into V. So notice that you can multiply by the multiplication in V and add by the addition in V, that this guy is a vector space. And it's a finite dimensional vector space because G is a finite group. So at least we're in that good shape. So the second thing is, how is this a G module? So what is the action of G on this space of functions? Right? So it's also G mod structure is given as follows. So if you give me some A and some F, I need to tell you what A of F is. Here, A is in G, and F is in the induced module. So here I used, notice that to check this, in this condition here, I've used that H acts on G by multiplication on the left. Right? So this is the equivariance with respect to H acting on G with multiplication on the left. So if I want to keep a G action here, I might as well only use the right action of G on G. Right? Because otherwise this is not going to commute with H. So I need to use the right action of G in X, which is good because I want to have a left action on this vector space. So whenever I have this, I'll define this as the new function acting in B, which is given by F of B times A. And I need to check that it's well defined. And I need to check that it's an action. So the fact that it's well defined, well, let's see. So being well defined, so I need to check two things. One is it's well defined. So I need to check that A of F acting on H times B, whenever H is an element in the subgroup H, well, this by definition is f on h BA. Oops, no. That's by definition. Now, by associativity of the group G, this is the same thing as f of h B times A. And by the fact that f was an element in the induced module, this is the same thing as h acting on f BA, which is what my definition was. So now this is h acting on AF evaluated at B. So I have that AF evaluated at H times B is the same thing as H acting on AF evaluated at B, which is this equation here. So okay, so my function A times F is a well-defined object in this vector space. And 2, now I need to check that this is an action of the group G. So now for every A, B, and now C in G. So what I need to check is that A acting on B acting on F is equal to A times B acting on F. So that's having a well-defined action. But then for these two functions to be equal, then this means that for every C, A acting on B acting on F evaluated at C should be equal to AB acting on F evaluated at C. Now, the left-hand side is A acting on BF evaluated at C, which by definition is BF evaluated at C times A. And now this, by definition, is F evaluated at C times A times B. And now on the other side, this thing here, by definition, is F evaluated at C times AB, which by associativity in the group G, these two things are the same. Okay, good. So I've just checked that this is indeed a G module. Now, if I wanted to have, so let's try to guess if this is going to be an adjoint or not. Okay, so I want to check whether or not I'm going to call this function F or G in the previous notation. So I want to check if this functor, which is the induced module, is left adjoint or right adjoint to this. And I also need to check that it's a functor that I haven't done this yet. But remember, so I think I kept them in the right order. Remember that, so probably I'll just have it here. Whenever F was left adjoint to G, what we had was a functor, a morphism from the identity in C into G composed with F, and we had a morphism in the other direction, F composed with G, to the identity in D. These are not symmetric statements. So what's easy to see quickly is that there is a map from the induced module to G of V. This is a vector space and it has its G mod structure. So from that induced module, which is that particular vector space, we have a map to V. Because these are functions, and G is not a set, but it's a pointed set. So whenever we have functions from a set with a preferred point into any other set, we have a map, which is the evaluation in that preferred point. So that's the fact that we have G with it, which is a pointed set. So whenever you give me a function here, what you do is you just give me f of 1, which is a vector in V. Okay, 1 is the element, the identity element on the group G. And, well, so I'd like to say that this is a morphism in the category of H modules, But then this is an H module, and this is a G module. This is not an H module in principle. So to view this guy, this same vector space as an H module, what I do is I apply that functor, which is the restriction functor from G to H, which didn't change anything because the vector space is the same. But now I'm viewing it as an H module. So now the question is whether or not this is a morphism in the category of H modules. And for that, I need to check what is the action of H on both sides. Okay, so for H, an element in H, I just defined you what the action was. Here is the definition for any element in G. In particular, it works for an element in H. So H acting on F is a new function. Okay? And now I map it to V, and it goes to H acting on F of 1. On the other hand, I can just grab F, map it to F of 1, and then act by H. Right? So F of 1, and then after that, act by H. And for this to be a morphism in the category of H modules, these two things should be equal. So I need two things to be equal. And yes, indeed, they are equal. Because this, by definition, is H of F of 1. By definition, is F of 1 times H, which is F of H times 1. And these two things are equal by the condition on the function F. Okay? So therefore, it means that we have canonically a morphism between this H module and this H module. So exercise, check that is compatible with morphisms. Morphisms from V to V prime in the category of H modules in the obvious way. So what that would mean is that we have canonically this induction gives us a morphism from the restriction of HG composed with the induction, oops, I'm using this induction tilde, induction from HG to, and it was in this direction, the identity functor in the category of H modules. Okay? Okay, so I say it here. So there is a candidate. If I put D to be the category of H modules, okay, I can see it from here. If I put D to be the category of H modules, C to be the category of G modules, then, well, in this order, F should be the restriction functor, G should be the induction functor, okay? And it seems that the restriction functor is left adjoint to the induction functor. That would be a guess, because I've gotten this morphism in this way. So instead of trying to prove that now, let's look at this other induction functor. Okay, so this other functor, it looks different, but it's pretty much the same. Let's see what property it is. So how is that a vector space? It's clear. Remember that K of G is a K of G k of h by module, meaning that k of g acts by multiplication on the left and k of h acts by multiplication on the right, and v is a k of h module on the left. So that tensor product that is written there by definition was a quotient of this vector space, which is you just take this vector space and you mod out by an equivalence relation. And the equivalence relation is that an element in k of g, v in v, and L, let's put some v, no, v is bad, S in k of h, then we declare that mu times S tensor v is equivalent to mu tensor S v. That was the definition of this space. Okay, so that's a vector space on the nose. And the question is, how is this a G module? And then, as a G module, it's clear what it is. It's just the multiplication by k of g on the left. Okay? So namely, for every A in G, we just define the action of A acting on the equivalence class of mu tensor V, we define it to be the equivalence class of AU tensor V. Right? The equivalence class under this equivalence relation. The fact that this is going to be an action is clear now because it's just associativity on the left here. There's not, I'm not going to check that, but we need to check that it's well defined. So we need to check that this doesn't depend on the representative of this equivalence class. But that's clear too, because if we choose another representative of this equivalence class would be, the generic representative of this equivalence class would be, let's look at this, for example. A acting on this class, tensor V. This is the same thing as A acting on U tensor SV. Right, so these are two the same classes. Here I just have by definition A U S tensor V. And here I have by definition AU tensor SV. And now the fact that it's associativity in this algebra, which is an associative algebra, tells me that this thing here is the same thing as AU S tensor V, and the class of this is equal to the class of this. Okay, so this is a well-defined G module. And now I wonder, I think this is fine, I defined everything correctly. So now I wonder if we have a map from that G module to V. But now it's easier to see the other way around. It's easier to see again because K of G has a preferred element. It's easier to see a map from V into this guy. Because we have a map from V into the induced module which just sends the vector V into the vector 1 tensor V. And so that's the difference between having functions, which looks like hom, into the tensor product. Okay, and now I can ask the same question. Well, this is an H module, this is a G module, to compare them and to ask whether or not this is a well-defined map of H modules, then I better take the restriction, which is just the same vector space. Now this is a map of H modules, and I want to know if this commutes with the action of H. Okay, so then if I have my vector V, I apply H of V, and then I map it. It's going to be mapped to one tensor HV. On the other hand, if I have my V, I send it to here, and I act by H, this is going to go to A, by definition, is the class of H tensor V. But the class of H tensor V is equal to this class. Huh? Therefore, this is also a map of H modules. And now I'm in trouble. Because now I have a morphism from V into, so I have exactly in the opposite direction. So again, exercise, just as this exercise here, check that this is compatible with morphisms. Check that this is compatible. With morphisms, and gives, well, now it's exactly in the opposite direction. Now I have a map from the identity. Well, perhaps I can now remove these two inductions. Gives a map from the identity functor in the category of H modules into the composition in this way. So it seems that I am in this situation where now I need to take C to be the category of H modules, not as before, which was D. And I have that this induction seems to be the right adjoint to the restriction functor. So it seems that this induction functor that I have by tensoring seems to be like the right adjoint to the restriction functor, and this other induction seems to be the left adjoint. I mean, if I'm hoping to get some sort of adjointness, these are the candidates because of those equations that I should get. So it looks like we have that the induction, right? So let's just check again that I got it right. In the first situation, right, which is a map into the identity functor, let's spell this out, the two situations that we have, just to make clear. So situation 1 is D is the category of H modules. F, well, C is the category of G modules. F is the functor, well, I have it there, it's the restriction functor. And the other function that is unfortunate that I called it G, for the same as the group, but well, G is the induction functor, but it was this induction. So it seems that the restriction functor is left adjoint to the induction with a tilde. And in the second situation, we have that C is the category of H modules. Okay. We have that D is the category of G modules. G is the restriction functor, and F is the induction functor. okay? Because I got them in the same order. So then again, it seems like we have that the induction functor looks, well, in here we got that the restriction functor being left adjoint to the induction functor on the left, and here we're getting that the induction functor from Hg being left adjoint to the restriction functor from Hg. So it looks like, which is what I have here, it looks like, well, the induction functor like this is left adjoint to the restriction functor, and this guy is left adjoint to the induction tilde functor. So that would be a guess. Okay, that's what we have here. Okay, but then there's the following issue. Let's analyze a little bit better what are these vector spaces. How do I construct these vector spaces? Okay, so what is the structure of vector space from K of G K of H V and this other functor which is functions f from G into V such that f of A, or let's write it like this, HA is equal to HFA for every H in H, A in G. So these are my two different inductions. So this one as a set is easy to describe quickly. How do you give me a function from G into V? Well, for any element in G, you give me an element. But on the other hand, I already know whenever you specify a function in any left coset for H, you get it on the whole coset, right? So this as a set is specified as set and as a vector space as functions from G mod H, and it's on the left, into V. It's clear what it is, right? So whenever you give me the element on any representative class, and you get it on the whole representative class. Okay? So this is the same thing as the set of functions like this, as vector spaces, is the same thing as a direct sum of a copy of V for every G of H. Right? So how do you specify a function from here to here? Just for each element here, you give me a vector in V, so you just get a sum of vectors. And here it's important that I have a finite group, or at least that this quotient is finite, right? To have a direct sum. Otherwise, I may have, I need to worry about difference between products and sums. How about this one here? How do we describe that guy as a vector space? But then again, the same thing. So K of G has a basis. E of G, where G is in the group G. And the same, similar for K of H. Okay? So then again, I can just move every element in H here to this side. So every element in G can be written, well, as the multiplication of choose a representative in each H coset, now on the right. Right? So we just choose a representative of each H coset on the right, and well, and now move the multiplication by H to the other side. So this guy here gets written as a direct sum of, well, those representatives of G, H times Z. Right, so these are, and now I ask the question, I mean, are these two spaces isomorphic or not? do I have a way of identifying left cosets by h with right cosets by h? I mean, these two sets clearly have the same cardinality. So as sets, they're isomorphic. So just choose any isomorphism. I'm sorry? Okay, so that's a question. So the thing is, these two vector spaces, we can choose isomorphism within the two vector spaces. There are vector spaces of the same dimension, therefore they are isomorphic. But now the question is, can we choose an isomorphism in such a way that these spaces are isomorphic as G modules or not? Okay, so there's a number of things that we can try, which I think I went slow enough and I repeated the previous lecture that I'm not going to have time to finish, so probably I'll just mention a few things and that I'll do next class. But we've learned that in order to understand, to pinpoint which representation we have, it's enough to understand their characters. So the one thing that we can try is we have these two representations of G, let's try to compute their character, their character. And the character seems to be very simple to compute. Because what happens? How does an element of h act here? When I multiply by h on the left here, what I do is I permute which coset I have. So I go from one v to another copy. Therefore, the trace of that element is going to have to be, well, it's easy to see what the trace is. I need to just only check which elements, when I multiply on the left, preserve the corresponding cosets, and then take the trace there. But that's a trace of an element in h in V, which is the character of V as an h representation. And I can try to do the same thing here. So computing the character is something simple, and that's what we'll do, I guess, next class. I was supposed to do this today. And then just take inner products of characters. But then there's other things that we can try, which, now that I have here this, let me just say something different. Now that we've realized that this space of functions can be viewed also as functions from left cosets into V, well, we have preferred functions. So, for example, we have the coset given by h. Right? So for each coset, we can just take a characteristic function. So in particular, if you give me a vector v in V, I might look at the function f that has values in G being equal to f of G if G is in H, 0 if G is not in H. Oh, f of G doesn't make any sense. G acting on V. So this function depends on this vector V, so I'll call this f sub V. So let's check whether or not this function is in the induced representation. Okay, so what I need to check is that f V of H G, well, by definition, this thing is H G of V if H G is in H, and is 0 if H G is not in H. But H G is in H, so here I'm assuming that H is in H. If and only if G is in H. And, well, this is an if and only if G is not in H. And on the other hand, this is the same thing as H acting on F sub V of G. Because this thing here is H acting on this thing, right? Which is clearly the same thing as this. So this is a well-defined function. So now I have a map from V into the restriction. Now I have a map from V into the restriction of the induction of V. Okay? Which is a well-defined map. It's a linear map. It's clearly a linear map. And now the question is this a map of H modules? Well, so let's check this. If you give me V, you map it to FV. And now you act by H. Okay? Well, it gives you this function here. So what is this function? By definition, this is the function that valuated at an element G is equal to FV of, remember, the action of H was by multiplication on the right, G times H. And now this function here is equal to, well, it's a different picture now. So this is G times H acting on V if G is in H, and 0 if G is not in H. So I started with a vector V, I mapped it to FV, and I acted on H, and I got this function. So now another thing I can do is start with my vector V, act by H, I get HV, and I map it to a function which is f of HV. And now this function here, evaluated at G, is what? Well, now it's f of HV. And I read it here. It's by definition G acting on HV if G is in H. And 0 otherwise, which are these two things, are equal. So this is indeed a morphism between V and the restriction of the induction as H modules. And that's a very natural morphism. So what we got now, and now it's again the same exercise. Check that this is compatible with morphisms, and you get a map from the identity functor of the category of H modules into the restriction Hg of the induction tilde Hg. And now this is in the other direction. So this would suggest that actually this guy is the left adjoint to this guy. Exactly the opposite of what we had. Right? If these functors were adjoint, then I would expect that morphism there. Similarly, we had a map from the restriction of the induction. I'm sorry. We had a map from the restriction of the induction without a tilde to V. Now let's construct a map from V into this thing here. Oh, I'm sorry, the other way around. We had a map from V into this thing here. How do we get a projection to V? But that's even easier, right? So I can look at this guy. We've written this guy as a direct sum of right cosets of V, and just take the projection to the coset of the identity. So let's check that this is a morphism of H modules. But that's obvious. So if I act by H, oops. Well, actually, that's a question. So let's see if this is a morphism of H modules. That's a well-defined maps of vector space. So I act by H. Right? Oh, the cosets are on the other side, right? Those were left cosets, here are right cosets. So I act by H on this guy here. So the action by H just permutes these cosets. Okay? So what happens? So if you have some G, some H, and you multiply here by H, well, so now you're in the coset of HG. And if you project, you might go to 0. Right? So on the other hand, if you just first project and then you act by H, well, then you're taking the coset of this. On this particular guy here, you project and then you act by H. Well, you're just going to multiply on the V side. So does this map commute or does not commute with the action of H? I've done it painfully in detail in the other case. So in this case here, is this projection into V? Does it commute with the action of H or does it not?
Because when you action in the coset that is not H, then it will be 0.
If you act on the coset,
if you action to GH where G does not belong to H, then HGH will be 0.
Okay, it goes. So if you act, so if you grab, okay, so continue.
So it's just because in other component is 0, whatever you do, you action H in other coset. So it's equivalent to add to just one way.
Wait, but the action of H is non-zero, right? The action of H is just permutes the cosets.
You take the projection.
Yes.
And all the other component is 0 except.
Correct. So that's correct. So therefore, we just grab this thing here. This is a direct sum, and then we want to understand what is the action of H on this thing. Okay. So the action of H on this thing is just by permuting this set of cosets. In other words, H acts by left multiplication on this set, and it acts by permutations on this set. Okay? And it acts by automorphisms. So the stabilizer of any point is trivial. So if I act by H on this sum here, well, it just permutes all of these components, and the only one that is fixed is the one that is a trivial coset that's fixed by the action of H. Right?
Maybe other set is fixed, but it outside the component, its projection will be 0.
Exactly. So it permutes all of these cosets. The one coset that is a coset of the identity is fixed. It doesn't get permuted, and it acts there by the action on V. Okay? So if I act by an element in H, it permutes all of the other cosets. It doesn't matter because all of them would go to 0 under this projection, except the one guy that acts by HV. On the other hand, if I just first project and then I act by HV. Okay? So that's the argument. So this guy here is also a morphism of representations. So again, the same exercise, check. So now we've gotten a map from the restriction Hg of the induction Hg to the identity morphism, the identity functor in the category of H modules. So before we had that, it looked as if the induction was left adjoint to restriction, was left adjoint to induction tilde, but now it looks like we have induction was left adjoint to restriction, was left adjoint to induction, like this. So now, lemma, or perhaps theorem. Let C and D be two categories. Let's just take F, a pair of adjoint functors. And let's suppose that G prime is also adjoint. Namely, we have F being left adjoint to G and F being left adjoint to G prime. Then G and G prime are isomorphic as functors. So there can only be one adjoint to a functor, up to isomorphism. This is just the same spirit of there can only be one inverse to a morphism. Can anyone guess why? Or what conditions should we add? So this would mean that we have this natural isomorphism. By definition, this is just natural isomorphisms in the category D from fx into y being the same thing as morphisms from x into g of y and being the same thing as morphisms from x into g prime of y. And I want to know if you already know this or not. And this is functorial. So I want to see why this means that g of y and g prime of y are the same. So in particular, if we just forget about f of x, this starts to look like it doesn't have anything to do with f. In particular, this is saying that morphisms in the category C from x into g of y are the same as morphisms in the category C from x into g prime of y, and this is true for every single x and y. If I take x to be g of y, yeah, so that's going to work, but which is not what I wanted to say, but yeah. So if I take x to be g of y, then this is going to give me a morphism from g of y into g prime of y, which is the image of the identity morphism here. So the identity morphism in g of y, under this isomorphism gives me a map from g of y to g prime of y. And the identity morphism, so that gives me a map. So why this is an isomorphism? You do the same thing. You just take x to be g prime of y. If you take x to be g prime of y, the identity element here would give you a morphism from G prime of y to G of y. Right? If you take x to be G prime of y, you would get an element from G prime of y to G of y. And these two morphisms are inverse of each other. I don't have time, I have only 5 minutes, so I'll let you to read something easier to see. So let me just tell you philosophically what's going on. Forget about, so I have this guy here. It's an object in the category. Just put any name. And I have this guy here. It's an object in the category. Okay? And I'm testing this object by looking at all the maps from a place from X into this object for every X. There's a lemma that says that this is the Yoneda embedding that essentially says that this identifies what an object is. If I know the set of all maps in a category from every object into my object, then I know my object. That's a statement. If I know all maps from an object into my object, namely, if I know the functor hom from every guy into my object that I'm trying to analyze, let's call it object. So understanding this functor, which is the same thing as understanding the object. So since these two functors are the same for the object G prime of y or the object G of y, then the objects have to be the same. So that's the spirit of the Yoneda embedding. And I'll ask you to read it. But your argument in this particular case also works. If you just take x to be G of y, then we obtain a morphism from G of y to G prime of y. And if we take x to be G prime of y, then we obtain the inverse of that morphism. So check that these two guys are inverse to each other. That's easy. So now we're in the following situation. We have these candidates, but there can only be one adjoint to each side. So if I have that these two statements are true, then these two functors should be the same. And then these two functors should be the same. So that gives us some exercise to check. Is it true that these two functors are the same or not? Otherwise, these two statements cannot be true. Okay? I have a couple of minutes, so let's continue with abstract nonsense, and this is going to be the last time that I do something with abstract nonsense. But just to check, when can we expect to have adjointness? So now I'm going to use the fact that my categories are special. My categories have sums, and I proved this. In the category of H modules and the category of G modules, we have sums, we have kernels, and we have co-kernels. We have a morphism of representations, then we have a kernel of representation of that morphism, and we have the co-kernel of that morphism. So for those categories, I would say that F from a category A and a category B is called, and let's suppose that in these categories A and B, I have these structures. I can sum objects, I can sum morphisms, and I have kernels and I have co-kernels. Is left exact if it commutes with kernels, if it preserves kernels. If for every exact sequence in A, this sequence is exact. But notice that I'm not adding the extra 0. It's exact in B. So that's called left exact. Namely, an exact sequence like this, what does this mean? It means that I have two morphisms, that the first one is an injection, the last one is a surjection, and the kernel of this morphism is the image of this morphism. So that's what exactness means for this sequence. Now, what does this sequence being exact? Well, it means that I have two morphisms. Well, this I always have. And the kernel of this morphism is the image of this morphism, and that the first one is in the injection. But I no longer have that this one is surjective. Not necessarily do I have that this one is surjective. The same thing for right exact. It's called right exact if it preserves surjections now. If the following is exact. Right? So the last one is surjective, and the kernel of this map is the image of this map. But this one no longer needs to be injected. I'll leave you this as an exercise because I don't want to take more of your time. But this is one of the beauties of the general abstract nonsense of adjointness. If you have two functors and f is left between any two categories where you can sum things, you don't even really need to be able to sum, but let's just keep it like this. If you have two functors and f is left adjoint to g, then f is right exact and g is left exact. So whenever you have two functors that are adjoint, then they have to, one of them preserves kernels and the other one preserves co-kernels. Therefore, if I wanted to check any of these two things, if this were to be true, then I immediately see something. Since the restriction functor is it's supposed to be, right? So this is suggesting that the restriction functor is left adjoint to one functor, it doesn't matter which one, and right adjoint to another one. So by being a left adjoint to something, it means that it should preserve co-kernels. But by being also a right adjoint to something, it should also preserve kernels. So let's add that definition. A functor is called exact. A functor is called left exact, right exact, and exact is if it preserves both. So we'd expect the functor of restriction to be an exact functor, but that's obvious because the restriction functor is just the same vector space. Of course, it's going to be preserving injections and surjections. Right? So it's clear that the restriction functor is an exact functor. But now I wonder, is the induction functor, so if this statement is true, then this guy would be, it's right adjoint, so this one would be left exact and this one would be right exact. And if this statement was true, then this guy would be right exact and this one would be left exact, the opposite. If both statements are true, then both would be exact and they will both be the same. So that's one place to start looking at. Is it true that this induction preserves kernels? Is it true that this induction preserves co-kernels? And then let's check. Okay, so that I'll do next time. But this is a very strong statement that is very simple to check. It's a very simple statement, and it's a beautiful result. Just out of abstract nonsense, whenever you have two adjoint functors, they have to preserve kernels. All right.